My name's Jay Gambetta. I'm an IBM fellow and I'm the VP for quantum computing. And today I'm going to talk about circuits. I wanted to start with a disclaimer. This is not going to be a lecture. It's not going to be any fundamental new research, but I'm just going to give you my feelings of circuits and a summary of a lot of the discussions we've been having internally as we try to answer the question of what is a circuit. Okay, so before I get there, let's go back and ask the question. Let's go back and ask the question about what is a quantum computer. Many people talk about it being faster. So here's a little chart to sort of highlight that this is not true. Imagine you have a problem and you want to multiply two numbers together, P and Q. And you ask, how long would it take this to be done on a classical computer, simple multiplication? If you follow these references and you take into account gate times and things like this and circuits for doing this multiplication, you find that the classical computer will be able to do it in basically a few milliseconds. And if we were to do the similar question and ask, how long would a quantum computer take to do that, assuming gate errors and whatever corrections going on, it would take much more, maybe as estimated in this paper that I reference here, 75 seconds. I don't want to focus too much on the absolute numbers, but the point here is really to highlight that we don't expect a quantum computer to be able to multiply two numbers and get faster than a classical computer. So it's not actually faster. However, if we look at the reverse problem, and we imagine that we're giving a big number, and we've asked, how do we actually decompose it into its prime factors? And it turns out this is a really, really hard problem, and it's the core to what keeps your encryption safe as you do things online and things like that. A classical computer for a 2040-bit number would take about 4.7 billion years to do it. And in fact, the biggest bit number that I know that has been done is this 768-bit number, which took approximately 1,500 CPUs. So obviously they parallelized over many computers. So now if you ask the question, how long would it take a quantum computer to do this? You get this answer of 8 hours. And you see here that it's not that it's doing the standard operations faster, it's a completely different way of doing it. And it's this different way of doing it that makes quantum computing so exciting. So if we ask the next question and say, what is a quantum computer? My colleague Charlie Bennett has this nice slide that I've borrowed here. And it kind of highlights that a computer can be thought of as stomach. And basically, you can think of a classical computer and a quantum computer as something that takes n bits of input and then does something magically in the stomach and puts out n bits of output. And what the difference between these two is the classical computer can only have an immediate state that has n bits, whereas the quantum computer has due to superposition and entanglement, it can have access to a very large intermediate state. And so it's like it has this ability to expand inside the stomach to do things that cannot be done classically. Okay, so to get to a bit more of this, the rules of the game for quantum computing basically say that if I have a system of initially n qubits, I need to be able to initialize it. So this just says I have the classical bit string, I need to be able to put in some value. Now, if then I have the ability in a quantum superposition to make a superposition of all of these, and then I have the final part to get out a probability. So this sort of shows the idea of that stomach that I talked about. I put in n bits at the start. Inside, I have access to this very large vector space. And at the end, I have the ability to sample some probability and get some outcomes. So these are the rules of the game and what we give an access. So as thinking about what a quantum circuit is, I'm going to start with what I'm going to call the purest view of a quantum circuit. Okay, so if we go back and we start at the beginning, a circuit actually is made up of gates. And the first gate that you will experience in quantum computing is the Hadamard gate. And this is a simple gate that allows you to make superpositions. So as shown on the slide here, imagine I have this gate, which we denote with a H, and I was to apply it to the initial state 0. It has the ability to make a 0 plus 1. And if I apply it to a 1 state, it has the ability to make 0 minus 1. So it has the ability to make a superposition with a positive superposition, a superposition with a negative sign. Now, you could think of this almost like classically as something random. I'm making a random state. If I measure, I get 50% 0 or 1. And if I measure the second one, I get the same 50% 0 or 1. However, if I apply this gate twice, and now I apply it to the first superposition, which we often call the positive superposition, I find that I get back the 0. And if I apply it to the first, I get back 1. So you see in this quantum, this gate, because applied twice, does nothing, has the ability to interfere itself and has the ability to cancel superpositions. And this is what makes these superpositions in quantum different to classical mixtures of probabilities. Okay. So this is what I was just saying. So the outcome of the first can be random. The outcome of the second can be deterministic. The second gate that we often see is the controlled NOT. And this has the ability that I can take a 0, 0. So if I have this gate, it's very simple. Depending on the input states, if I put a 0, 0 and apply this gate, I get back a 0, 0. If I apply it conditioned on the first qubit being in a 0, and I apply it and the second qubit is in the 1, I'll get back a 0, 1 again. However, if the first qubit is in a 1 state, when I apply this operation, I'll flip the control bit from either 0 or 1. And the same is true if it's in the 1, 0, I'll make the, if it's in the 1, 1 state, I'll flip it to 0, 1. So this gate will be the ability that we can actually make entanglement, which I'll give you a demonstration soon. The third gate, which we need, often is called the phase gate or the rotation around the z-axis. And this gate simply allows us to put quantum phases on our qubits. So it allows us to, if I'm in a 0 state, I don't apply a phase, but if I'm in a 1 state, I can put a phase on that. And this allows us to create complex numbers in our states. And this gives us the ability to do arbitrary rotations in this vector space. So a quantum circuit then. So basically a quantum circuit starts, as I said, with all the qubits initially in the 0. And then depending on how time goes from left to right, I obviously spelled right wrong on the slide, and each qubit, so each Y here represents a qubit. The number of qubits is the width. So how many qubits along here is the width. And you come across here on this first qubit, these first 2 qubits, and I'm experiencing a C0 gate. And then on this third and fourth qubit, I'm experiencing a C0. And then I have like an example of the Hadamard, example of this phase, C0, and at the end I measure. So with all these, we can build any unitary and make any state. I'm not going to go into this in this talk, but just say a quantum circuit is a way of laying down this. So let's just go through an example of a hello world program and show how we can make entanglement. Imagine you have first this quantum circuit where you initialize the first qubit in 0 and the second qubit in 0. And if you apply the Hadamard, you create this superposition as I talked about before. So now you have 0, 0 and 0 plus 1. Now, after we apply C0, we get to create the state 0, 0 plus 1, 1, and this is the entangled state. So here you see if I measure qubit 0, qubit 1 in 0 and qubit 0 and 0, I know the other, if I measure the first qubit in 0, I know the other qubit is in 0. If I measure the first qubit in 1, I know the other qubit is in 1. So you get this correlation that cannot be explained by its local parts. So as an example, if we flip over, here's a way that I've set this up that we can run it in Qiskit. So here I give you the ability, you can just come in and make your quantum circuit. You apply your Hadamard to your first one, then you apply a C0, a CX gate, which is the C0 to qubit 0 and 1, and then you can make the circuit as we described before. If we run this through our simulator, we can find that we can quickly simulate this and find that we get this superposition that I described before of 0, 0 plus 1, 1. We can add measurements, And then we can show that if we were to actually measure this 1,024 times, we would find in this particular run that it came out exactly equal, that 512 of them are in the 0 and the other 512 of them are in the 1, 1 state. And as can be seen, if I want to test this and run this on real hardware, if you've got an IBM account, you can easily jump in and run it. And what I'm doing here is I'm taking this circuit. First of all, I'm going through and finding the least busy of our systems that are online. It's turned out to be the Cambridge. And what we have to do first, if we are to run this on a quantum computer, is we have to be able to map this to the backends. I'm not going to go into this in too much detail, except to tell you that in our software, what we've enabled and what's one of the most exciting things that I'm seeing is you can make a new circuit from your previous circuit by just going through this compiler pass, which we call a transpiler, and it takes in the backend information. And here you see that because I chose to run this on a 20-qubit system, it's compiled this 2-qubit example into 20 qubits, on a 28-qubit system, where most of the qubits are actually in the ground state. And you see that it took this superposition and turned this into a gate that the backend recognizes. This gate here simply says on the backend, apply a phase change, then do a rotation to take you from 0 to 1, 0 to 0 plus 1, and then do another frame change, and then apply your C0 gate. And so you see that this takes account of all the backend information to give you a circuit that can actually be runnable on real hardware. I do want to basically, so here we see it's already run. I do want to point out that some of the most exciting work that I'm seeing from the community and the quiz kitters out there is the ability to come up with much smarter ways to do this compiling. And in particular, come up with noise aware is, I think, the most exciting one that I've seen from the groups out there that show that basically by taking into account what happens in the system, you can come up with more higher fidelity gates. Okay, if we run this on this experiment, I can show down here the results. And you see that the blue shows the predicted theoretical results, and the pink shows what ran on the experiment. And we see that they, on this particular one, they agree reasonably well, but there's actually a fair bit of errors that happen. And this is because I believe this is ran on the Cambridge device, which has a bit more errors than some of our other devices out there. But you can see that the experiment and the simulation predict reasonably the same results. So I would say this is your first hello world example of a quantum circuit. And if we go back, now we can sort of ask, what is an algorithm? Okay, so this slide here is trying to get at that idea and point out that an algorithm, to me, consists of first a problem instance. Then we need to have some way of describing this problem in terms of classical, like a classical algorithm, that writes this problem instance out into a quantum circuit. And at the end, we hope that when we run this, we get a solution that's classical. So you see here I come in with classical bits, and this can be related back to that stomacher that I said at the start. In the end, I get classical bits from my quantum circuit. And I hope that if I have a good quantum algorithm, basically everything in the problem scales polynomially with the number of bits. The way that I take the problem and rewrite it into these quantum circuits, and the way that these circuits then can be represented on quantum hardware is all polynomial in the number of bits. So I look at an algorithm as a way of making quantum circuits. So you can think of a quantum circuit under this sort of purist idea as a way of representing a description of how the hardware will actually run that algorithm. For us out there in the science field, we've actually come up with basically many different ways of classifying these problems that can have this efficient description. We call them BQP. So I do go back to my first slide and say it's not faster, it's easier to do these problems. And understanding these problems is an area in quantum computational complexity that I recommend for those that are interested, either go out and look at various different scientists' lecture notes. I personally like Andrew Charles's lecture notes that can give you different ways of understanding these algorithms. Here I've just taken a way of classifying them into 3 different areas, either linear systems, simulating quantum materials, so chemistry, and quantum walks, and such. So it turns out that there are actually a lot of algorithms that we know. The field, and we're continually finding more, and we're continually understanding how these quantum computers will happen. And actually, there's a zoo for quantum algorithms that I recommend all of you go check out. And there's actually a few hundred quantum algorithms out there, depending on how you count what is different, that are either algebraic, oracle, simulating, or some machine and optimization. So it's important that we keep doing this and understanding what we can run. But if you ask the question, well, why haven't we shown them yet? And this is because all these quantum algorithms actually require a quantum circuit to implement them that has near zero error rates. And the only way we know how to do that is actually error correction. And here you see why many people talk about, and including myself, the importance of bringing error correction in to get these algorithms, these idealized algorithms to run. And I just threw this slide in for a side note. Basically, error correction is expensive. Here's an estimate of running Shor's algorithm using basically qubits that are about 100 times better than the current ones. And you see that the numbers of physical qubits are quite scary in this. I will say that this is assuming one type of code. There is a lot of work that we're doing on coming up with more efficient codes, and this itself would be another whole talk of how do you actually come up with better, more efficient codes to explore error correction. But I want to change direction and come back to quantum circuits. And in the near term, there's an interesting part that is developed. And basically, there's these near-term applications, and they're heuristic in nature, and we need to be sure that they're doing something interesting. And so my view is that for the circuits that we're running on this hardware, the complexity hardness needs to go into these circuits, and only the circuits that are difficult to run will be the ones that we can hope to have a quantum advantage. Here I give a lot of references, and I'm not going to go into the details of these different types of circuits. And for a future talk, I'm going to, someone from our team will talk about what makes a circuit hard to actually run, what are interesting circuits. However, I will talk about a little bit what makes a circuit hard to simulate. So if it's easy to simulate, we know it's not an interesting circuit. So what we've discovered through various different research is that a lot of entanglement is needed. Otherwise, you can come up with tensor network contraction methods that can simulate these circuits efficiently. You need the ability to interfere to make these complex numbers and negative signs I talked about at the start. And it also needs to have some complicated algebra behind it. If it doesn't have all of these three and just has one of them, then it will turn out that it's actually easy to run these circuits. And as a demonstration, I'll switch back over to here. So what I'm going to do here is, and these notebooks you actually can find online in GitHub under my name, and there's a folder called there's a GitHub repository called My Notebooks, and there's a folder in it called What is Quantum Circuits. So if you're interested, please go over there and see about, look at them and how they run. So here I'm just making a simple code that generates basically a circuit. So the first circuit that I'm going to generate is circuits that are chosen to have all the gates that are either these X gates, Z gates, and a bunch of C0 and swap gates. So it doesn't really matter what the details of these are, except to say that these circuits, well, it turns out all these gates are from what we call the Clifford. So this is a Clifford circuit. So here I just randomly made a circuit of 5 qubits of depth 5. So 1, 2, 3, 4, 5. Okay, and the initial seed of 0. And here's what I'm going to do is I'm going to go through in the circuit and replace every one of these single qubits just with an arbitrary random single qubit generated an arbitrary rotation in the single qubit space to make the second set of circuits. Okay, so these circuits look very similar. If we take the first circuit, and here I'm going to make a new instance of 100 qubits with depth of 100. And you can see that I can run this, and in basically 1.3 seconds, I can get the results of this circuit. I'm not even going to try and interpret what's going on in this circuit, except for to say, basically what we've done here is shown that circuits of this form are actually very easy to run. Whereas if I was to run this circuit, and what I've shown down here on the bottom is just scaling versus number of qubits, the difference between running the circuits of the first form and the circuits of the second form, and you see that you see the difference between an exponential and a polynomial scaling. So if we go back to what the talk that I was saying, you see that there are circuits that can have a lot of qubits, they can have a lot of depth, they can also create a lot of entanglement, but they're still simple to simulate. And then there are circuits that look very similar to these circuits, but because they don't have the structure that we can exploit these Clifford circuits, they're actually difficult to run. And as what is shown on this next plot was what I showed on the notebook, you can see there's a very big difference between these two types of circuits. So what we know is that there's a growing list of circuit families. We're working to put lots of them out there. And each one of these circuits are either good for benchmarking a quantum computer or exploring some computational task. I don't want to say too much other than to say, I see the need and the future of building a circuit library that we can bring circuits to people to investigate either how to make those circuits better or to use those circuits in some computational task. So my thoughts from a purist view is a quantum circuit is a description of how a quantum algorithm runs on a hardware. And what makes a quantum computer hard to simulate is not the number of qubits, not the gates, but the quantum circuits it can implement. Okay, so that's one view of a quantum circuit. So now I want to take a different lens and say, what is a quantum circuit from the view of a rebel? So imagine now that I want to run this algorithm, and I have this matrix H, and I want to find the minimum eigenvalue of that. It turns out that this is important in chemistry and many other types of optimization problems. And if I can estimate this energy, and provided I can minimize this wave function to find the minimum energy H, I will be able to find this minimum eigenvalue. And this is easy to show because the properties of the quantum wave functions and the properties of the Hermitian operator that is used to describe the problem. So as an example, I can write this H out in terms of what we call polyoperators. It really doesn't matter what they are, but they're an efficient way to write them out for something that can work with qubits as a bunch of coefficients and a quantum operator. As an example here, I've taken a case of just a simple Hamiltonian that is xz plus zy. So the first step is to write it out into something a quantum computer can understand. The second step is to choose a trial wave function. Hopefully this can be based on some reasonable assumptions. In general, this is complex and probably the weakest part of the quantum eigenvalue, the variational quantum eigensolver. But by understanding which ones of these and coming up with different trials, we can work out how to inject different types of circuits into to this algorithm. Here I've just given an example, which is 2 qubits. That's parameterized by arbitrary rotations over the x-axis, arbitrary rotations over the z-axis. This creates different types of phase. And then the C0 gate that I talked about before that creates this ability to create entanglement. So this is creating an arbitrary single qubit rotation on qubit 1, an arbitrary single qubit rotation on qubit 0, an arbitrary qubit rotation on qubit 1, and then some gate that entangles between them. The next part is if I can write H in terms of Pauli operators, I can then calculate the energy by simply measuring these different Pauli operators. And I can measure each one of these different Pauli operators by adding to the circuit a different rotation in the single qubit space that allows me to create a new circuit. And then by simply combining the results together in a way determined by the Pauli operators I want to measure and the Hermitian operators, sorry, the weighting coefficients H, I can calculate this energy. To go back to that example that I had before of XZ and ZY, I want to measure these two. I can measure Z by simply just doing nothing on the qubit 0, and I can measure X by simply applying this Hadamard operator that I talked about at the start that flips you to the superposition spaces. So you can see that I can then calculate, measure this first component by measuring the probability of being in 0, 0, probability of 1, 1, minus 0, 1, minus 1, 0. Then the same can be done for the second operator here, but now I have to do slightly different circuit where I apply some phase followed by a Hadamard to measure Y. And then this can then be combined to give the second operator here. So you see this VQE as a program basically starts to look more like I make a bunch of controls and then I generate different circuits and then I combine them together to compute some energy, and then I come back in time and make new controls. And each time I do these, I'm making a different set of circuits, and I just follow this loop repetitively many times. So this doesn't feel like a quantum algorithm that was the circuit that I gave in the first case when I looked through the lens of being a purist. However, the rebel can say, well, I could just imagine that I just put all of these circuits together, and now I just have a bunch of classical bits that I make. I first make my first set of controls, I make my second set of controls, and then I estimate the cost based on the outcome of this, and then based on the cost that I've estimated, I make the new set of controls, and then I estimate my final cost, and I could repeat this many times. So the rebel would say that anything that can be done on a quantum computer is a circuit. So my thoughts on this is giving a circuit the ability to perform arbitrary classical calculations feels a little bit like we're giving it a bit too much power. I think it's not needed. And if we were to force ourselves to force the circuit to control the quantum data between the different realizations, we're overcomplicating it. So what I think we need to do and what we're working on is we need to define this new concept of near-time computation, which basically says that on some type of host computer, we allow some calculations to be done, and those calculations make new circuits and combine them together, and eventually this would be an algorithm API. So my thoughts are, I think the rebel is going too far and that VQE is not a circuit. However, there is a middle ground. And the middle ground I'd like to call the practical. You now have the situation where you want to do some classical computation. So a typical example that everyone that gets into quantum, one of the first things they'll see is quantum teleportation. And you imagine that you have a qubit, Alice, and you want to send some information to Bob. And you imagine that there's a third qubit that can generate an entanglement resource to allow you to send, by just using classical bits, a quantum state from Alice to Bob. If you want more details of this, I totally recommend looking at the QuizKit textbook, and there's a section on teleportation. So the way the teleportation works as a circuit is you first have a part where you initialize the qubits, a part where you generate the resources, a part where you measure, and then a part where you do some classical computation. So if we go through this, I put some arbitrary state in, and the first two qubits are in the 0, 0. And so now I have the quantum state in qubit 0, and I have the two other qubits, qubit 1 and qubit 2, in the 0 state. Now I entangle qubit 1 and qubit 2 to create a Bell state, similar to the quantum hollow world I talked about before. And now I have the qubit still isolated by itself, and now this quantum resource that is connected to it. Now what I can start to do is entangle qubit 0 and qubit 1. When I do that, I find that the state that I can get will have the state now in the third qubit with qubit 0 and qubit 1 in the 0 state. It will have the encoded qubit with a negative error between the superpositions, with the first qubit in 1 and the second qubit in 0. It will have a bit flip. It'll have the state with a bit flip error that is applied, and it will have the fourth option will have the state with both a bit flip, so I flipped 0 and 1, and a phase flip, so I've created this negative sign. So now you can see that if I was to measure these two qubits and I get 0, 0, I can do nothing, and then I can have my quantum state. If I was to measure and get 0, 0 for the first one, 1 for the first one and 0 for the second one, I then go through and just flip it and apply a Z operator, and this takes this negative sign and creates back the initial state. So if I go through all of these, depending on the outcomes, I can then apply classical controls and get always back the quantum state that I originally had from the start. Okay, so here it sees that by giving my ability to do some classical thing, I can make some problem tasks easier. Here's another example, which I'd like to thank Andrew Cross, one of my colleagues that helped put this together. Imagine I want to make a very entangled large resource state, which we call GHZ states, which is all the qubits in 0, 0, 0, 0, and all the qubits in 1, 1, 1, 1, 1. Okay. So if I just had a linear chain, I would have to go through and make, say, the first qubit here 2 and create it in a superposition. Then I entangle qubit 2 and qubit 3. Then I entangle 3 and 4 and 2 and 1. And then I entangle 1 and 0 and 4 and 0. And then I can measure it, and I've made my GHZ state of all the qubits either in the 0 state and all the qubits in the 1 state. And if I was to calculate how fast I could make this, the depth of this circuit would be linear in the number of qubits. So now you can sort of say, well, imagine I had the ability to do some classical processing. So now, instead of actually doing the problem where we first create the entanglement and swap it all out, we create all the qubits in the zeros, in the plus states. So they're all in 0 plus 1, 0 plus 1, 0 plus 1. And now what you come in and is you imagine measuring the parity between the first two qubits and the parity between the next two qubits. And depending on the outcome of the parity, you do some classical logic that flips the qubits that are measured. And a way to sort of see this, if I measure the first parity and I get a value basically that both the qubits are not in the same state, I apply a flip. Or if I get both of these in not the same state, I can apply a flip. So here's a table that sort of gives this concept. If I was to measure 1 and measure 2, I would do no correction, because that would mean that these would have the same parity, these would have the same parity, and so the output state would be 0, 0 or 1, 1, 1. If I was to measure that this one had a slightly different parity, one had parity 1 and the other one didn't have parity, I know that which qubit I need to flip. I need to flip the first qubit, and so then I can do a correction that flips it. And the same is true for all the different outcomes. This actually, for those that know, is what we call bit flip code. It's not quite an error correcting code because it is only correcting for bit errors. But you can see, I could imagine that using this as a resource that allows me to take some superposition and create an entangled state. And what happens is now you can see I can reduce the depth of this circuit to constant and not require the linear that I talked about. And while I'm now trading the ability to do these parity measurements, and I haven't into the detail of how to do them, but usually what we have to do is introduce an extra qubit that we can then entangle with these two neighbors and determine, and that allows us to measure the parity Z1 and Z2. So as an example, I can show this example. So, and this example is nice to run. I'll come back to the top. So here, this example gets to highlight some of the tools as well. So I'm going to make a circuit from swaps where you basically apply the different C naughts and make it out by swapping each one as you create the chain, the circuit from parity, and I'm also going to introduce the ability to put noise on our model. And so here's the example of the first circuit showing the swaps. Here's the example of the second circuit, and here you see the parity that I didn't talk about, where I imagine that I create this one and this one in a superposition, and now this one is measuring the parity between 0 and 2. This one is measuring the parity between 2 and 4. But you see this circuit is not growing with the number of qubits. It has the constant depth. And now, if I was to simulate these, I would simulate the first one using the stabilizer simulator that I talked about before, and I would find that basically I would get, as expected, the outcome associated with the GHZ state. Here, I've simulated and now done the classical post-processing to calculate the GHZ state that would correspond to the correction that would happen from the shots that you measured. And now you can do something really interesting, and you can look at, as I put on noise. So here I've imagined that I would apply noise to the idle qubits, the 2-qubit gate, and the measurement of about 1% on each of them. And when you go through and do this simple simulation, you can see that there could be, at getting a larger number of qubits, say around 50 qubits, a difference between doing the quality of doing, say, a constant depth versus doing the swap. So you see that by giving yourself the ability to add this extra resource, you can do the same task more efficiently. And I didn't have time to give another example, but one that I would recommend is iterative phase estimation. This is a nice example that shows that you have a problem where you want to estimate the phase of a unitary, and you know the eigen vector that you put in. And by doing the measurements, you can condition future operations to give you a faster way of estimating, extracting the phase from a quantum circuit. So I think what this points out, if you can use a classical resource to make something more efficient with higher fidelity, we should use them. And we need now to define this new concept, which, to make it different to near time, we're calling real-time compute. And these should be all the classical primitives that you would want to do that could be done very close to your hardware, and done, the key here is done within the coherence time, so you can use them to improve the operations of your circuits. Some of them could include classical plus minus, multiply possibly, and some ifs, some if loops, like for the error correction. Something I didn't talk about is repeat until succeed type circuits, where you could use a while. These are to determine how you get an outcome and continue doing it until you get it. And the goal of this is what we're envisioning for our future version of OpenQASM, and we're working on trying to update it to give you more control flows. So I would say, after thinking through this, I think of the quantum algorithm as the ability to generate circuits, to use circuits that have the ability to do classical operation, and also on the top to have the ability to do, on a host computer that is close to it, to do all these classical extra functions that we call that I call near-time compute. And in the end, we get out a problem solution. So just to give a summary, here's a slide that my colleague Ali put together. So here you see the different control flows. So you have the purist that sees a quantum circuit as simply a way to represent a quantum evolution. You initially reset, you apply all unitary evolution, and you apply a final measurement. So I would call this the standard wiki type view of a textbook. Here you see if I've got classical resources, why not use them to make my task better as a sort of medium or the practical definition of quantum circuit. And then down the bottom, called the rebel, the one that would view VQE as a circuit. In this talk, I've only just gone through the basic building blocks, but you can even go further. You could even go, imagine that I believe that a circuit has the ability to do very large functions, and I want to abstract anything to large libraries like Boolean functions or more advanced phase estimation type inputs that are used in this metropolis sampling. These, you could imagine that a circuit is more of a high level abstraction, and you could take the rebel even further and say that VQE, when I don't even know how to decompose the ansatz, is also the definition of a circuit. And then to complete this, you can even go lower and view that signals on wires are a circuit, or you could say pulses with feedback could be a circuit, or you could take the complete rebel in both the control flow and the basic blocks and say, I have no scruples, anything that I can run on a quantum computer is a circuit, including a word processor. So in my view, these are the things that we want to enable in quantum circuits, so we can work out how we can make either compile better circuits, work out how we can make libraries to use different parts of circuits. And this is the focus of what we're doing and building out of a quantum circuit. So we've put a definition of a quantum circuit down. I'm not going to read through it, except for basically to say it includes the unitary operations. It includes the ability to do real-time classical computation. It has to require, like the purists require, the ability that it can do a universal set. And in the end, I hint at that a quantum program needs to be represented by circuits and this non-concurrent classical computation. I will say that not everyone in our team is agreeing, and we're continually discussing. Some of us are purists, some of us are rebels. I'm finding myself in the center. So in the future, I think we're going to continue this live stream with talking about different ways to simulate circuits, how we can build near-term applications from a circuit, how do you benchmark a circuit, and how do you use a circuit library, as I hinted at, to build more complex circuits. Okay, I wanted to thank everyone, and I believe I've never used a live stream. Now I can answer questions. Yeah, so I'm going to stop sharing and switch over to some of the questions. Yes, please. More insight on the phase and how it refers. So the quantum phase, so if you were to actually think of phase, so if I make just all zeros and all ones, that's basically what we call a classical state. So I can have any combination of them. What matters to really get the power of quantum computing is to be able to create superpositions. So I need to create a superposition like 0 plus 1 or 0, 0 plus 1, 1 or other superpositions like that. If all of my superpositions are positive numbers in my state, then there exists a way that I can use advanced simulation methods like quantum Monte Carlo to simulate the outcome of that state. So I need the ability to make negative numbers or complex numbers so that I can interfere and use interference in my algorithms and my circuits to make my ability to get a quantum, like to get something that I can't mimic with a classical computer, a quantum advantage. So the phase is simply a way that we can control putting a a complex number on our states. Physically, the way it's done is simply by applying a frequency change or a frame change to our qubits, such that in the middle of the algorithm, they are experiencing a different phase to what they may be experiencing later. So the question is there a relationship between QAOA and VQE? I would say they are converging to a similar thing. The original QAOA tried to make an ansatz on a given, like an assumption of exactly what trial states it would go in. However, what they're both evolving to is apply a circuit and minimize the different trial functions for the different Hamiltonians. The difference between classical sort of optimization problems and chemistry problems is the operator that is used in it, the Hamiltonian, is either diagonal or so all z's, or it is in the chemistry, it's these more complicated polys of x's and y's. I'm skeptical personally that in the diagonal sort of form that we are going to be able to find too much quantum speed up, because those problems have, when they give the final answer, a classical state like 0011 or something as the output. Whereas we know that the output of the more complicated chemistry, like or material or quantum problems with x's and y's, require a quantum state that cannot be represented classical. This, well, the third, could we say that question again? So the question is, will the third generation of OpenQASM be closer to a programming language or a hardware description? Yesterday, we are continually internally having this argument, and I think the ideal solution is a compromise of both. We want it to be human consumable and the ability for it to be easily read and maybe even written by hand. However, as we try and advance more complicated control flows, it suggests that we need to start to give the language a bit more information about the hardware. And a nice point is you could imagine even tiers in the classical hardware where certain parts are done much faster than others. So you could imagine that if it's a simple classical function, there is something that's really close to the systems that can do that. Whereas something more complex, like doing the parity check that I just talked about, it goes up to another stage that is still close enough that it can be done within the coherence of the system, but is a more complicated function to estimate. So I think the answer is we're going to try and achieve both. However, I view that Qiskit and programming languages like that and Python, we shouldn't reinvent a language for the standard way of controlling. We should exploit the great classical languages like Python and the many other ones out there to do the more higher level tasks. Yeah, so just to give a shout out to all the people that are interested, we're going to, the YouTube channel is at Qiskit. Follow it, and you can get you'll be able to see many more of these sessions that can talk about more details about circuits. Plus, also there's a lecture series and how to program quantum computing. Yes. So the question is it possible to do tomography with Qiskit? So tomography is another example of a a program where you generate a lot of different circuits, and then those different circuits you bring together and you process in different ways. And it can be either done by taking into account some assumptions about the hardware or quantum. For instance, we know that the states must be positive semi-definite. So you put constraints into your reconstruction. Those are generally done with a classical algorithm. So what we've done in Qiskit is we've built into the Ignis element the ability to make those different circuits for tomography, plus also the ability to explore different ways of combining those circuits back together and processing them to explore the ability to reconstruct the state. And tomography itself and benchmarking quantum systems and how you work out what's going on is a question that I've been scientifically, personally doing for a long time. And how you handle statistic, systematic, and various different errors go into the reconstruction phase. And I would recommend anyone that is interested in tomography to go check out the Ignis section, the Ignis part of, and the examples there, and there's still a lot more work to be done on better reconstruction methods. So the short answer is yes, it's in the Ignis element, but tomography is a hard question in general. So the question is, how does it feel to see the transmon successfully working, and what is the next step? So the transmon is a qubit that I was involved in when I was at Yale, working with Steve Gervin and Rob Sholkoff. I've had a love-hate relationship with the transmon. It's great to see that it continues working. It has a lot of benefits. One of them is its stability. So when we make our systems, because we're stable against both charge and flux noise, we don't have to tune them regularly. And so they're calibrated not that often, maybe once a day. And so it has the stability, but it comes at a cost. And its cost is a loss in atomicity. We knew this when we first invented the transmon, and we talked about that we get charge stability with an exponential more stable, and a polynomial loss at its atomicity. The atomicity has always become limited in how fast we can do the single qubit gates. However, generally, we've come up with control methods, and for those interested, the standard is that we still use is the drag method, that we can remove the effects or mitigate the effects due to leakage in the single qubit space and still get high fidelity operations. In the 2 qubit space, the loss of atomicity puts severe constraints on and tolerance on how we fabricate the qubits. So the future, well, I think the transmon will stay around, but I think we need to keep thinking of, at the same time, more exotic qubits, hopefully with the same level of stability, or different architectures that don't have those constraints, or even different gates. And these are all the science that we actually continue doing at IBM.